Hello everyone, this is a video for module KV7006 Machine Learning. This video is for dimensionality reduction. So some of you have already learned big data. In big data, one of the challenges is that big data normally has a large number of features, or in other words, dimension. So high-dimensional dataset normally will bring a lot of problem in terms of data analysis. So you may find the image analysis is a typical data analysis with high-dimensional dataset. So because image or video has been represented in multi-dimensional features which represent color, depth, or relevant features of image or videos. So that complexity is much more than what we have learned. For example, in big data dataset, you already have a limited number of features which have already in a structured way. Sometimes we consider image or language, natural language, or video are unstructured dataset, which normally have dimensional or missing data, or with not the normal representation of the object. So sometimes you will find some features are missing or additional feature will come out. So there will vary of a number of features on different records. So that is complexity of high-dimensional dataset, also in context of big data. So our goal is to find a low-dimensional, yet with a similar useful representation of data, which means given that the original dataset, if we can reduce some features, probably they are less important, or sometimes even irrelevant, or sometimes some features only bring noise rather than any useful information into our particular data analysis problem. Therefore, we need to reduce some features. So you may ask me, given a dataset, is there any general way to reduce dataset? Yes, there are some methods we are going to learn. We probably will learn theory, you will learn practice in workshop. However, sometimes some features can be removed, reduced, for particularly data mining problem you are having in hand. However, in another situation is that you may also find some features which are less important or almost irrelevant for almost all machine learning problems. So in the material, this video or the next one, principal components analysis, will not focus on particular machine learning problem. Instead, we are focusing on general features which are less irrelevant to the dataset. So in the end, we are going to use less number of features, which is a dimension. But however, this less number of dimensions still contain meaningful or useful information for us for analysis. So we have already, or you have already seen some visualization in the low-dimensional data structure. For example, we have learned or seen time series. So in time series, you have x-axis represent the time, y-axis represent the change of values over time. So we can see, for example, some of you have done some exercises about the crime, number of crime, we can see is increase or decrease over time. So that will give our some insight what's moving on the number of crime over time. Another benefit of have less dimension is that we got less chance to overfit. We have better generalization. However, this also brings a problem of the accuracy. Probably you will see that accuracy may reduce. So that is always a problem of balance. But normally fewer dimensions will have less chance of overfit. For example, we have learned in previous videos, we have learned the decision trees. In that, if we have less number of features, the depth of the tree will be, mathematically will be less than we use more number of features. So the tree will be simple, and then we have a less chance to be overfit. And also, this will have a speed of learning algorithm if we have a smaller number of features. Just like the example I just mentioned about decision tree. Imagine I have 10 features or I have 3 features. You can see that immediately 3 features decision tree will have us to generate or process much quicker than if I have 10 features. So there's problem about the scalability. So scalability is important idea in terms of use of computational resources. I'm not going into detail of the complexity or big O notations, but I would mention here is that, so imagine I got now 3 features. So I got a certain unit of computational resources to generate a decision tree, for example. Now, another case, I have 10 times more features than my original dataset. Then the computational resources I need in order to generate a good decision tree would be more than 10 times than what I did for 3 features. So they are not completely scalable. So the reason we need to understand scalability is that when we do large-scale system analysis, we need to estimate the computational resources we need, and in order to manage the resources. Certainly less storage. So this is also relevant to speed. So we got less storage to process data, for the data compression, etc. So here we put a note. Dimensionality reduction is different from feature selection. Although their goals are kind of same, so feature selection is to try to, like say, I got 10 features. I select certain features and use for certain particular task. They have some similarity, of course, but the features and the dimension are not always exchangeable. In some cases, we will see example later on. So dimensional is more like extraction. Extraction also includes construction. There's another kind of concept. So we will construct small set of new features from original features. You can see construct means you create something. So if you're really interested in the feature construction, I have published some academic research papers which you can see some example on feature construction. Well, we based on existing features, we did some modeling. So therefore, we can, in one hand, we can reduce number of dimension, but on the other hand, we can use a model as features rather than just a single variable as features. So if you're really interested in that, you let me know. So for dimensional reduction, the first concept is a linear one. So I put everything, quite a lot of things in this slide. It's a linear dimensional reduction, so LDR. In the next video, we will see principal component analysis. These two are relevant, but they are different. So let's see what linear dimension reduction is. So basically, we have multi-dimensional data. This method will help us to project our data in a linear way. So if the data itself is, have a linear subspace, so they are nicely, for example, we all know what is linear models, for example, linear regression. We all know that you can use a line rather than a data set to represent the trend. So if the data itself have good representation into a linear model, this will be good approach. So for example, if we got a data set which is a real data search space, have a dimension like many dimensions, okay? So we want to project to k dimensional. So k is smaller than original dimension. Let's say originally we got a 20 dimension. That's d equivalent to 20. Let's say it, and then now we have a k dimension. Let's say 2 dimension. 2 means xy dimension, or let's say 3 xyz dimension. A vector. So we were going to use a 3-dimensional vector to represent original 20-dimensional original dataset. So this is also a way of do approximation. So they are not exactly the same, but we use projection of the original data to 3-dimensional, here k equivalent to 3, data to represent original dataset. So it's also kind of modeling. So there will be a vector. There will be a vector which is you can see now R is a real data space. K equivalent to 3 is a simplified or representative model of my original model. So U is the project matrix, because I originally have 20 t equal to 20. Now I have 3. So you can also think of U is a k-dimensional subspace. So we got here x, y, and z. This is 3-dimensional. You can see the diagram. So the output U will be 20 of times 3 project matrix. So here you can see we got a lot of points. So instead of use original point, we got them into this subspace. So this point, I will find their projection on my U space. So this is grid, is my space I used to project it. Because it is, we cannot do more dimensional because it is image, okay, or plot, okay. So we can only represent 2-dimensional here. So we project that into, you can see every point in original samples projected onto this grid space. Okay, so actually we wanted to show you that we have one group, another group, another in different color, blue, red, and green. So there are different methods, certainly, how U is defined or learned. So we were not going to give you too much detail here, but the concept is in this diagram. So you will see you can define different methods into when you use packages. So the difference depends on the property data we want to capture. For example, it all depends on the data mining problem you want to look at. Certainly, if you define this classification problem, it will certainly different from the regression problem. So that really depends on what we want to learn from the data set, what model we want to build out of the data set. So I think previously in one of the video I have mentioned that generally in machine learning there are different kind of models. For example, we have already learned distance-based model, for example, clustering. So, we always talk about the calculate distance between center and the sample, calculate distance between different groups. So, distance-based. So, I have already made a video on decision tree. So, there are tree-based models. Okay, most of you have already learned linear regression. So, you will know regression or linear-based models. And then you also, probably somewhere, you also learn logic-based. I'm teaching a module which is formal method. So which are logic-based models. So if that is rule-based. So logic-based is use logic operations. For example, the very, very mature program language called Prolog. So they are logical operator-based. And the rule-based is relevant. It's also relevant decision tree. For example, if weather is good, we are going to play football. If weather is bad, we are going to study in the classroom. So this is a rule-based. So you can see we got different type of the problem or output models you want to look at. So certainly different models as output, you would look at the different part or different property of the data. So the purpose of data analysis would be different if you want a different type of models. Okay, so now we are going to give you some example to see how it works. Sometimes it works well, sometimes it may not good enough. So this is two-dimensional data. We got x1 and x2. So these blue dots represent our data set. So each data point has two features on these two dimensions. So if we ignore the x2 for each example, what would it look like? So you just think we ignore x2, everything projected to x1. What it would look like? I give you 2 seconds to think about. So ignore x2. So each data set, originally I have, let's say, a data point A, I have 2 values. One is, say, 10. My x1 equivalent to 10. My x2 equivalent to 1, say that. So I got 1,000 of data set. Now I only consider x1, ignore all the data of x2. What will be look like? Just give 1 second to think. What is image will look like? So okay, so if we ignore x2, they will become a line. So the only difference is on one dimension, that is x1. So you can see you scratch every point x2 equivalent to 0. Let's say then you only got x1. Then you only be able to compare on x1 dimension, which a lot of data will be the same. So you will lose a lot of information because end of the day you will find a line, you will lose a lot of information without x2. So in this case, it's not good way to remove x2. So we still need x2, and x2 cannot be removed or reduced. Just give me a second. Okay, so this is another example. So this is example 1. This is example 2. So these have different distribution on the dataset than the original one. So it's like can be so both relevant to x1 and x2. Okay, so now consider this example, the second example. This is also dimensional data, also have two features, x1 and x2. So now we also try to ignore x2, for example. So let's imagine we project every sample only on the x here. For example, this point I only got here. This point I only got a value here. This point I only got a value here. This point I only here. So all project on my x1 Excel. So because I removed x2 dimension, do you think we'll lose a lot of information? Yes, certainly, because that again will be aligned without little information on Excel. X2 Excel. So actually for this diagram we can see that because this dataset is very relevant to both x1 and x2, therefore we cannot remove either of them. Now we look at the third example. The third example is, you can see we change Excel now. So we change to U1 and U2. Okay. Then we still have two features, U1 and U2. Now imagine you ignore U2, just ignore U2, and then you think about what it would look like. So anything is represented by U1. So do you think this will lose a lot of information or not? So imagine, so what I'm going to say, so U1 and U2 here is a coordinate system. So end of the day, we still work on x and y dimension. So if we look at this, imagine we switch this whole chunk of dataset to align, which align with U1. So they still represent the values on x and y dimension. Is that a little bit? I think that need further explanation. So look at this one. Every sample will become x1 without any information on x2. So, but here we change the coordination system. So basically, you can see is use a regression model represent the dataset. Although not perfect, but they have general trends which represent the whole trends of the dataset. So you can imagine this one is based on XY, traditional XY dimension. So I generate regression model. This regression model is like very good because they project nicely on the U1 dimension, which is my linear regression model. So I use a line to represent the dataset, and that line have a certain angle or degree, have a certain degree, which best represent their trends over the two-dimensional space. So in this case, I wouldn't say they will lose some information, but they will be good representation of the dataset because the whole data is spread over the regression model, which is nicely represented by U1. So the variation is calculated by distance among, from distance from U1, this linear regression model, to all the space. You can see, because the shape of the dataset, you can see the distance is very small. So that is a linear model to reduce dimension. So it all depends on how we designed the space which best represent the data. So we have seen several examples. This one. So you will say, these are same data, but you can see I change the dimension. Imagine I change the dimension here. I use linear regression model to represent that one. So all the data are projected on my linear regression model here. So in summary, basically is if the data is represented nicely, original data is represented nicely in linear way, I think it's more or less in linear way, because the x2 dimension have very small variance. They are very nicely, very small range of changes. So if this good linear way original data, the linear dimension reduction will be a very good approach. So the next video, we will also learn dimensional reduction, but we are going to know a different model called principal component data analysis. Thank you very much.